But probably not going to need it, right? So thanks for joining. Some of you might have been like talk that we did about stream processing generally. So today, and like I was just saying to someone before, I don't really know what the workshop format is meant to be. So I'm just going to take this as an opportunity to run deeper into kind of like how the stuff works that we were talking about yesterday, if you were there. And sort of like be able to field questions as well, and maybe slightly more interactive. So the session is about squeezing value out of your data. I'm going to talk a little bit about the value that you can get out of data, and where you get that value from. But then we're going to be focusing really on looking at a running stream processing application that's using ksqlDB for processing. And essentially, like I'll run through what the use case is, but it's going to be a customer 360 loyalty kind of points. Of course, that's a very specific thing, but really, hopefully you'll be able to see kind of like how it generalizes out, because Customer 360 is a specific example of like basically any business object being spread across multiple silos. Right? So to start with, I'm going to start with the this idea of kind of like the value you get out of data, and fast data, which is sort of like what Kafka does. Not the only thing it does, but it's a big thing that it does. Fast data versus big data. And so big data, as you can see here in the graph, it's got a kind of like a value graph that the more data you have, the more value you get out of that data. So you can start to see patterns, you can start to have like certainty around, or more certainty around kind of like the inferences that you're drawing from that data. And that's great, but we also have kind of like fast data. And so when I say faster, I really mean the ability to react and process data quickly. And we sometimes say real time or near real time, depending on who we're talking to, because there's different understandings of, you know, in finance it might be like nanoseconds, but we're talking kind of like millisecond latencies, those kinds of things, you know, up till maybe a second. And so the value curve is very different. So when you start looking at fast data, the value starts decaying very quickly over time. Essentially that means like the longer it takes for you to react to that data, the less potential value you're going to extract from that data. Classic example is fraud detection in financial services. So you present a card, if we can get a response back in sort of like sub-second response to fraud, that we can insert that into that kind of like the whole process. Somebody's willing to wait a second to have an approval for their card. But if it's going to take 2 minutes, clearly it can't be used in the same way. And so we're back to that idea of post-processing transactions and identifying the ones that were potentially fraudulent as opposed to just blocking the transactions. And so that's kind of an example of that fast data. Now, currently a lot of organizations are sort of like taking their operational systems and plugging them into sort of like big data warehouses for analytics. And we kind of suggest that that's still a use case that, you know, we don't replace big data with Kafka, but what we would sort of like say is that you can actually have Kafka as the integration layer that is capturing information from databases using things like change data capture, and also software as a service products. Basically, like pretty much any system can be captured through Kafka and then actually pushed into your data warehouse. So what we've done then is we've taken the same data. We're extracting the big data value, but we're also extracting the fast data value. So we're actually getting more potential use cases and value out of that data. Now, along the way, and this is sort of particularly relevant to what we're going to be talking about today, is this idea of stream processing. So the idea of being able to actually not just pass this data through, but do something with it in real time as part of that flow. And then, of course, kind of like the other aspect of Kafka is this notion of infinite storage. So what we see now is a pipeline where we've got your source systems. They're going through, we're extracting that, we're doing that sort of like real-time analysis on the data, we're extracting that value, creating those use cases. But then we're also using Connect to push into the data warehouse. But then when we look at this, we think, well, you know, the data warehouse is one possible use of that data, right? But it's not the only possible use. So big data just becomes another kind of downstream consumer of that data. And it's a very important one, but it's not the only one. It's used for typically analytics and reporting. And so this idea that big data is kind of like the only destination for that data that's moving through a fast data loader is probably flawed. And so we see kind of like lots of use cases around like cybersecurity where we're actually doing some real-time processing on the data for signal and signature detection. We're also filtering out data and we're aggregating things and pushing them into Scene. And then of course we're moving data into cloud, sort of like into cloud services, so like Lambda functions and that kind of thing. So all that integration can happen through Kafka because all the data is actually flowing through Kafka. When we add in that persistence layer, that's where things become really interesting because Kafka moves from just a sort of like a pipeline for moving data. It actually moves to kind of like, well, this is going to be controversial, but a source of truth across the organization. What we mean by that is that Kafka becomes the point of integration. So, just wanted to get that out of the way. Confluent and Kafka kind of like represent this kind of like all of the bits on the left-hand side of this diagram. One thing, because like the workshop is a bit more practical, there is a site, developer.confluent.io. We might have time to look at it, but it's actually got a lot of these what we call stream processing recipes, but also patterns for working with event streaming, because it's a new technology and it's a new kind of like programming paradigm. And so one of the things kind of like that's really useful about this site is it's got all the introductory information, but then it's got patterns for building or solving problems that work with event streaming. Of particular interest in terms of ksqlDB is it's also got some stream processing recipes. And so these are kind of step-by-step examples of how to build out a simple stream processing application. And I say simple because they are kind of like, I suppose they're simplified, but they're taken from real use cases where stream processing is being used. The nice thing is, and again, we'll have a look at the slide at the end, but you can actually, there's a sort of like a single click which will launch it in Confluent Cloud, so it will guide you through the tutorial on Confluent Cloud. Confluent Cloud, like this, like you can either scan this or you can just go to Confluent Cloud. The $400 of credit is just credit that you get when you sign up. No credit card required, all right? So like we're not, you don't sort of like forget about it and suddenly you've got this huge bill. It will sort of like last for 30 days or credit. And if you listen to the podcast, streaming audio podcast, they actually give out coupon codes to extend that credit as well. So you can actually go through some of the stuff that we're doing today and try it for yourself in your own time. Okay, so I guess like moving on to today's use case. I'm going to have to keep track of time somehow. I don't know how. Somebody give me a 5-minute warning or something. With what we're going to be doing today, okay, I shall connect to the whiteboard. No, it's still there. There we are. It's just not gone into full screen. So this is kind of like the output of yesterday, but what we're going to be looking at today is a quite specific use case where we have kind of, like I said, it's going to be around the customer. And so we're going to start off with kind of customer loyalty events. All right? And so these loyalty events are basically being generated at point of sale. So somebody swipes a card at a vendor, and that is recorded as loyalty points, and they're added to the customer's account. There's also going to be kind of like a customer system. And this customer sort of like system, it tracks kind of like information about the customer. That's actually in a MySQL database. All right, so that's kind of like, so what we've got here is got this idea of fast moving data, because this is going to be like a constant stream of events. But then we've got like what we might consider kind of slow moving data. This is like updates to a customer, which, like happen a number of times per day, but we're not talking about hundreds of times per second, most likely. But we also bring in this idea of really slow-moving data. So this is customer credit information that is sourced from an external vendor and provided via a CSV. So this is kind of batch data, right? So the challenge here, all of these things are kind of like relevant in terms of my customer, but the challenge is kind of like how do we actually integrate those all So we end up with this notion of customer 360. All right? So we're going to be walking through that in the example. During the example, I'm going to be using Confluent Cloud, so we're going to kind of like use that to view kind of the queries that are running. So, to start with, this is an example of Confluent Cloud. So what I'm looking at, Confluent Cloud is organized as kind of like a hierarchy. You get an organization, then you create environments. Typically they'll be sort of like prod, dev, or maybe a line of business. Within an environment, you can have multiple Kafka clusters. And so this all runs in the cloud provider of your choice. And you can have kind of like new clusters in different cloud providers. And so I can create a cluster. There's different types of cluster. And then I will be choosing the cloud provider. And I'll also be choosing which region I want to deploy that to. So that's all under a single account, so you can have a multi-cloud strategy. I'm going to cancel out of that. And I'm going to look at a running cluster. So here we see kind of like the customer 360 cluster. And I get to see sort of like some throughput metrics because I'm producing data into this cluster. The first thing that I might want to do, though, is kind of like understand a little bit about the topology, kind of like what topics we have. And so the way we would do that is to go through sort of like a data catalog. And so I might put in loyalty because I'm interested in loyalty events. And I can see that I've got some schema relating to loyalty. But I've got this kind of like topic which looks interesting, global loyalty events. Right, so we can just take a little look at that. And here we're now looking at a topic. And this topic has kind of like sort of like bytes being produced and consumed. And we can go in, we can kind of like look at the messages as they flow through. And we can see the schema that's associated with these events. But really, I actually want to see kind of like where these loyalty events sit in terms of our overall data topology. So anyone who was in the talk yesterday, we sort of like talked about that idea of like processing data through a topology. And so I can view this in what we call stream lineage, and I can actually see that this data is coming in from a particular data producer. And that is my, remember this is my loyalty points. Okay, so I'm actually generating kind of like loyalty points. The actual implementation, because we're in a workshop, we can talk about this, the actual implementation is just what we call a data generator at this point. So a data generator will produce data at a rate that we define and a schema that we define allows us to build and test our systems. That's going into a topic, and so I can kind of click and I can see what's going on in that topic and get some metadata. But the idea is that I can actually view sort of like the lineage of my data and where that data is going to. And relating to some of the stuff that I was talking about before, we can integrate at any point. So you can see here, this topic branches off into 3 different sort of like sub-branches. So one of these branches, I'm actually just pushing this straight to DynamoDB. So this is going to a cloud service, to a database, to do whatever it is I'm doing in that database. And that's just sort of like consuming from this topic in the same way that these other sort of substreams are consuming. I can also change my window of time, so I can sort of like look at, you know, where data has moved into the system, kind of over the last 12 hours, and I may not have actually pushed any different things into the system over the last 12 hours. No, I haven't. But this gives you an idea of kind of like the data that's in the system. But we really, like, for the focus of this, we want to talk about the data coming into Kafka from these source systems and how we process that. So to start with, I have kind of like, I suppose, a source system here, which is MySQL. This is running in Docker, and I'm running CDC in Docker. And then it's actually pushing through to Confluent Cloud. And then eventually, this all comes back to a local Mongo database. And that's driving this kind of like, this customer kind of like interface where we can actually see kind of like the updates to the customer in real time. But to understand how this application is built, we need to go into basically ksqlDB. So ksqlDB is a stream processing technology, and it's built to be kind of accessible to people other than Java developers, all right? So there are non-Java developers out there who still want to do stream processing. And so this introduces a SQL-like syntax for building stream processing applications. And so, you know, we have an interface to basically test and write our queries. But this is also exposed via REST so that you can actually deploy queries via REST. But the important thing to understand at the first bit is to understand kind of like, well, what is the flow within ksqlDB? And so what we see here is three basic sort of like stream processes or topologies here. So we have our customer raw data. And the customer raw data, you'll notice the sort of raw, this is the data as it's coming in from the source system. Now you may remember that I said it was using CDC. So CDC, change data capture, it's a way of integrating with a database very efficiently. So it uses the internal database logs to capture changes in the database rather than querying the database itself. So it's a very efficient way of actually capturing data, but it does produce data in a format that absolutely makes sense, except it's not a very nice format if you're a developer and you're asked to work with it, because it's specific to the capture method. So we can actually have a look at what this looks like. So here, I don't know how I can actually increase the size, but we can actually look at, get it pretty small there, but we can sort of like increase that a little bit, and then my interface is going to be very hard to use. But so what we see here is a typical of a change data capture sort of like data packet. So we've got a before state, so you can see kind of like what the object looked like before. We get the after state, all right, so that's what after the changes, what the object looks like. And we get some metadata about kind of like how this was produced via CDC, which system, which tables, kind of like a lot of the information about, you know, what was happening in the database at the time that we captured it. And so you can see that this is all very useful. But if you wanted to say to your developer, well, this is the data schema for kind of like, you know, building off customers, it's not going to be a great conversation. Nobody's going to want to work against that. So the first thing that we want to do here, and I'll just go back to sort of like normal Zoom, is to actually clean this up so that it can be shared at the domain boundary. So if we think that we've got kind of like a sort of customer domain, they're responsible for maintaining kind of like the customer records, they share that data at a boundary. At that boundary, that data has to be cleaned up. And so if you recall kind of like the previous schema, you can see now we've got the same data, but in a much cleaner format. So it's kind of like quite neatly structured as a JSON object with kind of like a nested address object in there. So we've gone in real time from kind of like that big ugly structure into a very kind of like clean structure. And the way we did that was with this create stream statement. So the create stream, again, like the interface probably doesn't love being zoomed, but this is the query that is persistently running, that is actually waiting for new events, and when it receives a new event, it processes it and creates the downstream structured event. A lot of this is going to be familiar to anybody who's got kind of like any relational database experience, all right? So you sort of see things like kind of like, you know, select statements, and you can basically see the common pattern for a SQL query. We introduced some new kind of like some domain-specific objects here, kind of like this idea of a stream. Okay, that's something unique to Kafka. And just incidentally, because it's kind of like probably important, we talk about topics and streams, and they're kind of sometimes used interchangeably. The topic is what Kafka stores. It's the log of events. A stream is kind of an abstraction we place over the log of events to allow us to interact with it. All right, so the first thing that we do, if we have a topic that we want to expose to stream processing, is we create a stream around it. We wrap it in a stream, which gives us all of the programming kind of interface to actually work with it. Oh, is that? It's not time already, is it? No. What time is it, incident? Oh, actually, I've got
2 o'clock on the dot.
Okay. All right. We're going okay. So
the stream is a transformation, or it allows you to create a view. You use the database term, it allows you to create a view.
well, the stream itself just kind of like is an abstraction that allows you to do that. Yeah, it doesn't do anything. It almost doesn't do anything on its own. It just gives you programming methods against the topic to allow you to interact with the events as they move through.
So it just exposes it to action, so you can, like you said,
Yeah.
play with it.
Yeah, exactly.
Yeah, so it's pretty much a view.
Yeah. So it's just and so we like the first step is always kind of like creating this stream, and so we can see that. And I'll just go back to here. We can see with loyalty events, maybe we get a very similar thing. So we're getting our loyalty events coming in, but with our loyalty events, if we zoom in on that, no, that wants to do something very different. Wants to do exactly what I wanted, but very slowly.
There is a plus and minus in the corner.
Yeah, that it doesn't zoom the text for the actual. That will zoom the graph, but not the interface text. And this is the bit, yeah. So there's kind of like this, which is our loyalty event. And so I'm going to try to. No, it doesn't want to do that. Maybe if I'm not focused on. Sorry, guys. Loyalty events. I'm going to try it one more time, and then I'm going to abort. All right. So a loyalty event comes in, and it looks like this. So the loyalty event has a transaction ID, as you'd expect. It has a customer ID. So it's got a notion of customer, but only at the ID level, so it doesn't store anything about the customer. And then it's got some points associated with the transaction and the vendor that issued the points. The credit's kind of like similar, but it's just pulling in kind of like credit information about data. And I don't think I've pushed any data through there recently, so I have. So we can see kind of like credit is much simpler, where we've got customer ID, a sort of like a credit score and some kind of bankruptcy field, which we would tag as PII. There'll probably be a lot more PII fields, but we might tag it as sensitive so that we can actually obfuscate that downstream, so that when my call center pulls down this object, they don't see anything about a customer's credit score. Okay, so what we've done here, we've gone from these raw things, and with loyalty events, what we're doing is that we're actually casting. We're just doing a simple cast where I need my customer ID to be stored as a string, and the loyalty system is putting it through as an integer, and so I'm just doing basically a very simple cast here. And that's sort of like allowing me to sort of like work with that data downstream and join, because now I'm joining on the same kind of like types. So then I've moved to this kind of global stream. Now I've used a naming convention here, probably not the best naming convention, but this idea of global means kind of like this topic can be consumed across the organisation, right? There are other ways of actually kind of like tagging these topics in terms of where they're made available, what SLAs they have behind them, and that kind of thing. So when we sort of like, again, start talking about data mesh, what we see here is we're kind of building up our data products that can be shared, all right? And so we've got kind of like this global transformation. And then we start to do some kind of like stateful transformations, all right? So up until now, we're just processing event by event, all right? So it's just kind of like I don't need any context beyond seeing the value in an event to transform the shape of that data. But there are some transformations where I do need to create kind of like a stateful view. There are also some technical reasons why we do this as well. But what we see here is we have our global loyalty events, and I've got like two sort of like streams that flow out of this stream, right? Both creating a table. So the first one here is actually events by vendor for 10-minute windows. All right, so essentially what that's doing is it's monitoring the stream of events, and it's creating an aggregate in a 10-minute window by vendor. So it's basically grouped by vendor. So what it's saying here is Qantas, and this is all fictitious, by the way, I just so we're, yeah. Qantas, kind of like within this 10-minute window, window start, window end, has actually issued this number of points. And so that windowed query, again, is just created by this SQL syntax. In this case, though, I've actually defined what we call a tumbling window with a 10-minute span, all right? So a tumbling window, there's different sort of like types of window that we can use. But a tumbling window, basically, they're adjacent but non-overlapping. So they'll always be kind of like 10 minutes, 10 minutes, 10 minutes. We can also, I haven't done it here, but we can define a grace period. So we can say a tumbling window of 10 minutes with a grace period of 5 minutes. And what that allows us to do is wait for late arriving events. So they will still form part of that earlier window, even though they didn't arrive in time, kind of like in the sense of when that window notionally closed.
So just a quick question, just understanding. So as the data was coming through, it kind of always told me, oh, it's firing every time like an event's coming through. But what you're actually saying is that because of these keywords here, it's actually automatically triggering itself every 5-10 minutes. So that's
it's actually constantly processing. So it closes the window, but like I suppose the nature of these persistent queries is that they're long running, they're always running, and every time an event comes into the system, it's processed. So it doesn't process. The tumbling window doesn't say to the query, process this every 10 minutes. The tumbling window, you can actually inspect it and you'll see that it's sort of like building up its aggregates and its averages. But after 10 minutes, it closes off.
Yep.
And then kind of like whatever was in there
is then saved.
Is kind of like the result, yeah.
Oh, okay. So it's just doing its math in the background.
Yeah.
And instead of saying, I'm going to wait 10 minutes until all the data's been snatched and then go, okay. So it's
which is one of the reasons we can actually keep up with fast-moving data, because
so it's effectively a bucket. So as the bucket's full, new one comes in and starts filling up.
Yeah, kind of. Yeah, and those are always available. And like the nice thing about all of this is that it's backed by topics.
Yeah.
So in terms of Kafka, it's got a layer of persistence. And an interesting thing is these stateful stores, they're actually stored in memory on the brokers, but they're persisted to disk on the brokers using RocksDB, and they're persisted to Kafka in a distributed manner. So that's really important when you need to rebuild state, or you need to know that your state is actually being captured and is not going to disappear. And that's something when you think about a message queue, where a lot of the storage is just in memory and it's not a distributed system. If you lose a kind of broker, you may lose what was in the message queue. So, we've just seen kind of like we've actually diced that up into a 10-minute window by vendor, but we've also actually taken exactly the same stream and we've organised it in terms of global loyalty events state. And so this loyalty events stream, so we've got two tables coming off this stream of loyalty events. One is being split up by vendor, 10-minute window. The other is actually doing kind of like the latest state over the entire history of the topic and organised by customer. Okay, so now we've got the same data that's being organised by different keys, basically. So if we have a look in here, we see an interesting thing. Well, I think it's interesting. We see kind of like we're introducing sort of stateful aggregations into the data object. So now I have my customer ID, so that's just coming through. I've got the number of points for the transaction, all right, and the vendor. Okay, so that's all the kind of like in some ways stateless. That was just what was in the event. But then, and the transaction ID. But then we're actually calculating the total points for this customer and their average points per transaction. So we're kind of getting a little bit of a mix of kind of like of data in here, because we're getting some sort of like stateless and some stateful. And we're also creating kind of like tables against things like our customer. So if I look at my customer, I now have global customer state. And for those of you who were in the talk yesterday, this is that bit that I was talking about sort of event sourcing. So the notion that I consume all of the events, and as I go through the events, I'm building up state until I get to the current time, which is the current state. So now what I have here is the current state of my customer, and every time there's a change to the customer database, this state is going to be updated. And again, we do the same for the credit, which is just a little bit less interesting. Okay, so now we've got these kind of like this sort of like topology where we're capturing, we're cleaning up, we're potentially adding state. But this is where kind of like the really important stuff happens, where we actually take those three sources and we turn them into the customer 360 object. So as you can see from the kind of like the graph here, these topics are all getting joined together. And if I go into the end message structure, what we see is it's a composite of the three systems upstream. So we can see that this information here looks like what we were just looking at, which is the customer information up to date. The latest loyalty transaction is actually the most recent transaction that this customer has made. The loyalty points here are coming from that fast-moving data again, but they're being aggregated statefully. So now I know my customer has X number of points, loyalty points. And then finally, we've got our credit rating score that is coming from those CSVs. Now, the kind of like, the nice thing about this is that these queries kind of like, they don't run at a point in time. So if you think about a relational database, you run a query, and that query really is capturing the state of the system at the time that the query is run. And so it gives you kind of like a result. And that result kind of like isn't going to, isn't going to change or update. With stream processing, these queries are what we call persistent. So they keep on running. And they keep on processing events as they see new events. All right? So when I change one of these upstream systems, so if there's a change in any of these, my customer's database, if I upload a new spreadsheet, or when I receive new loyalty events, the state of that final customer 360 object changes. So I'll stop there and I'll see if there are any questions, and then we'll go into kind of like we'll go into the risky bit where I try to update one of the source systems locally and we watch it update and the whole system works.
I'll probably have a bit of a question about this whole data aggregation, because I've worked with a system that has everything in one database, customers, documents, all sorts of stuff, and the information gets updated over time, and there's huge transactions, and we've had to update things on the inside. You're saying, at least with the systems here, my example might be a bit of a terrible one because it's all done in the one database, but we could probably use something like this to actually hook into that database, do all that transformation and pump it out somewhere else, so that the data that's sitting in the location, all the work hasn't been done on that one machine. We can take away that extra compute of transforming and updating all the rows and just let this create that final state. So it might not go back in, but it'll just be a second database sitting side by side to something else. Yeah.
Apart from the last bit, I'm not sure. So it will be sitting. Actually, it might be. The example might show you kind of like how it ends up in another database.
Yeah.
There's still a system of record. Like maybe that helps. So if I'm working in an old mainframe, that will still be the system of record for a business application, and that business application may be updating the records in the mainframe. But when those changes happen in the mainframe, they're actually offloaded.
Yeah.
And they basically flow through and update the state of
because at least with our example, it's more the case that we have, everything's all relational and links. If you update the customer, it's just a record into one database. But then as you start querying the data, it starts creating these huge data maps that take forever.
Yeah, exactly.
So something like this could just be a little more simplified because you've grabbed that information as you need it on the fly and you've put it somewhere that's a bit more reasonable. So
and it points to kind of like, we talked about event sourcing. There's another thing, CQRS, which is Command Query Responsibility Segregation, which is an incredibly clumsy term to say that you separate your reads and your writes.
Yes.
So, so you're kind of writing into the system of record, and then when you need to read for a downstream application, it reads from a different system. Yeah. So that's CQRS.
And the other thing too as well, I'm sorry to be digressing a bit further as well, it's more of a case of tracing data errors, because we've had cases in our system where data gets lost in the transformation process due to whatever reason, and it becomes really hard to find the data because it takes forever to query it. So something like this, if we can have a second system that looks at all those changes, and then because at least we can de-identify data with certain transaction IDs, we can find exactly where it faltered, and then send that data back so we can listen out for those particular keys.
The really nice thing is that with data persistence in topics, you can actually replay. So if you've got an error in a business application that has actually rippled through downstream systems, you can fix the error and replay the data. So you've still got the source, access to the source events. And really, you know, at this level, this customer's raw level, this is the source event. And so whilst we may not want to use it for our operational systems, we want to store it so that we can actually reuse it if we have to, or if we want to bring on a new system that wants access to this data. So, like, it's very powerful capturing those raw events, because they are, when the whole idea behind, I suppose, event streaming is that the business is described by a series of events. So those events are core to kind of like what happened in your business. Yeah.
A good replacement for SQL Profiler.
Yeah, okay.
I have a question.
Yeah.
So the final state, the global 360 view of customer.
Yep.
Is that a view over the event store, or is it a persistent view, persistent state?
Yeah, great question. So if we look to the final global customer 360. Yep. And so this is kind of like both a sort of like, I suppose, ephemeral in the sense that it's kept in memory, but it's backed by a Kafka topic. So in fact, if we look at the create table query, we've probably got in here, we do, it says with Kafka topic equals global customer 360. So if I go into my topics, I will find that there is actually a topic called global customer 360, which is the same as any other topic. And we can actually look at that. In fact, we're going to be looking at that as we test the system. So we can actually see that this is actually receiving messages.
If the system were to go down, that data is still able to be read at some point, right? Like if Kafka goes down, all that data is lost.
If it does. Sure, if it does. Yeah. No, the data's not lost, it's a distributed system. So this data is stored in it's configurable. By default, it will be stored in 3 different machines or brokers. Those brokers typically will be in different racks in a single data center, or they'll be spread across availability zones in cloud.
Yeah, okay, so there's high availability.
It's high availability, yep.
So
yep. If we lose a broker, everything just keeps working.
And if someone wanted their own system using actual Kafka itself, you know, because that's containerized, you can have your own high availability locally if one chooses.
Yeah, exactly, yeah. And that also gives you parallelism. So a lot of the fact that Kafka can produce a lot of data and like it's got incredibly, trillions of events per day, is due to what we call sort of like partitioning, and the fact that we can run parallel consumers. And we can scale those out as needed, and Kafka actually handles the rebalancing. So if you add a new consumer into your kind of container, into your cluster, Kafka will recognize that, and it will start sending messages in a way that actually guarantees ordering. So it doesn't actually lose the ordering by adding parallel processing. So a lot of smarts under the hood. So let's see.
So just one question. So the global customer 360 is unique to your customer record set. It's not keeping all the previous events in that.
Well, that's a really interesting point. It actually, every time there's an update to any of those source systems, I get a new event in my global customer 360.
Okay.
Right? So it's actually got an event for every change that happened in those systems.
But it's also created another record that says this is my now updated.
Yeah, so it's got kind of like, it basically has a key value store, and it updates the key value store to say that this is the most current aggregate. Yep.
So it becomes it's a unique customer, so I can find my unique.
Yeah, in fact, I think we're about to see this. Yeah. So what I've got here is kind of like the MySQL database. Again, it's running locally in Docker. I've also got Mongo running locally in Docker. And then I've got this application that is built off Mongo. And so what we're going to see, I'm going to actually open up, I'm going to go back to ksqlDB. we're going to go to the global. Well, actually, we can even look at the sort of like the global customer stream as an example, and we can view the messages that kind of like appear here. And so I'm going to update a customer. So I'm Jackie Herrera. So I'm going to update that record. And actually, before I do that, I should also bring up the record in. What was her ID? Sorry. ID was 1. So if we sort by ID, we've got Jackie Herrera here. So this is in MongoDB locally. This is in MySQL locally. If we just like update the address, so she's called in, said actually you've got an error. It's street. And so I save that. That's actually gone through Confluent Cloud. It's come back to my laptop, and if I refresh this,
there you go.
So that was just, I refreshed it, so it actually queried the database again. So that bit was kind of like MongoDB doesn't auto-refresh. And if I actually go to my front-end system, which in this example might be a call center system, all right? So the idea of actually constructing this object was so that we could actually power a call center application. We see Jackie Herrera, and if we go in, we can see that she now lives in Ducklington Street. And so I can also see all of my latest transactions. Okay, so that they can call in and they can say, okay, I need to validate your account. What was your latest transaction? We can see that here. We can give them information about their total loyalty points, the average loyalty point per transaction. This is all coming from 3 different systems, but it's being aggregated in kind of like real or near real time. So let's just like test that, and let's say let's say she moves to a more sensibly named street, like George Street.
Duckworth Avenue.
Right, I know. And then we go into our front end and we look at Jackie Herrera, and that's updated now. So what just happened then was I updated a MySQL database, CDC captured that change, pushed it into Kafka topic. That went into stream processing. That was actually processed by all of those kind of like steps. It updated the global customer 360 object. It pushed it back down to MongoDB, and it all happened through a 4G kind of like connection, and it all happened pretty quickly. Like, yeah. So, and I think like, do we finish at 2:30? It's a 50-minute. On 2:30. Yeah. So what I might do is just quickly show you kind of like this developer site, because it's got some, so this is the developer site that I was talking about. So the things that I think are really useful, you know, there's a lot of great courses about learning the basics of Kafka and of event streaming. When you get more kind of like used to those basics, there's also, and they've changed all of they've changed kind of like this navigation, but there I see it, we've got a pattern library. And so once you become familiar with the basics, you're going to want to solve some problems. And so you might come here and look at all of these different patterns that apply and when you use them, right? So it's a really useful way of expanding your understanding so you can actually apply the knowledge. But finally, we've got like in the, I think we'd have in learning, what I'm looking for is the stream processing. I'll tell you, I'll go back to the home page and I'll do it the way I always do it, which is to come down and kind of like explore top use cases. All right, and so what this page is giving us is lots of streaming recipes based on real customer use cases. So we can see here we've got anomaly and pattern detection. We've got some actual use cases around Customer 360. They're not the one that I just used, but they'll be kind of like probably slightly simplified versions. Areas of cyber security, etc. So if we actually click into these, you'll find that it actually talks about the problem statement, but it also gives you a kind of like a button that allows you to launch this demo in Confluent Cloud. So if you sign up for that free, no credit card required kind of like account, you can then launch a use case in Confluent Cloud, and it will sort of like walk you through all of this. But we also, in the tutorial, we show you how to create the stream processing topology that actually makes them run. So I think kind of like that covers the major things I want to get through. Are there any kind of like questions or reasons why this isn't going to work? Yep.
Quick question for the materialize or visualization for the database. Instead of actually publishing another topic, different ways to, for example, like directly connect to view what's the
Oh, right, yeah. So yeah, like I mean, we use, you know, like how do you get data into Kafka basically? Yeah. Is that the...
No, actually, so for example, those data now sitting inside the ksql database. Instead of materialize into a topic, which eventually sent to a database, is that way I can direct connect to the database actually?
Yeah, there is, yeah. So what we've shown is an example of what we call push queries. So a push query is where we run the ksqlDB query and it pushes down to the destination system. And so in the case of MongoDB, we didn't really, we did look at it. This is kind of like being upserted, so the individual record ID is being pushed every time there's a change. But ksqlDB also has a REST interface. So you can basically query by key, or for a windowed aggregation, you query by key and time. So you can actually say, okay, well, show me what my customer state was last week, because that will still be stored. Yeah, so you can actually do those pull queries, which is like, there are cases where that's really useful, and there are cases where the push queries are the, yeah.
What's the possibility? I know this is a bit of a stretch and a bit of a silly idea, but let's say if Confluent and all the data capture stuff just went down, but the raw stuff was still live and the endpoint was still live. There's a big patch of data that's, you know, the processing is obviously not working. A whole bunch of raw data has been updated, and downstream the end can't receive it until the thing goes back up and Confluent's back up. Data's been updated, Confluent's back up, and Kafka's back up. How does any of those data changes in the source database push its way down into its target database when in that outage time? How does it bring out to date?
Yeah, so Kafka and the whole ecosystem really is designed around the idea that network partitioning events happen, right? Like we lose connectivity to some system. So with CDC, remember CDC is actually using the internal database logs, right? And so the sort of like the point which defines where the RPO, right? So like the recovery point objective, the point, where, how much data you lose, is pretty much defined by the retention period on your CDC logs. Okay. So we would typically, with a customer, when we sort of like integrate CDC, we would also suggest you probably increase your retention from 4 hours or whatever to 7 days, which means you can have 7 days of outage, and as soon as the system's back online, it's actually going to start from where it left off. Okay. Yeah. And the really neat, I think it's really neat bit about this is that all of that state, like actually understanding how much it's read from that database, is actually pushed back into Kafka. Yeah. So kind of like if my connector is fried, like the machine it was on is gone, and I have to put a new connector in, the first thing that connector does is it connects to Kafka. It says, okay, what am I processing and where was I up to? Yeah. Yeah. So it kind of like that can die and be replaced, and it's stateless.
There's a state manager that's saying, okay, I'm at this point, so therefore, if I've lost my self-connection, I can just replay in order, because obviously those transactions come in one by one. Just go as far as it can to seize all the states it needs to go, and then by the time it should be up to speed. So it would at least honour that time duration, so it doesn't kind of go out of sync. It's actually in order. Yeah, it
will process it in order as if nothing happened, like the window. And for different connectors, so CDC is kind of a nice one because we have logs, and like increasing the log retention time, it costs some disk space, but it buys you a lot of security in terms of business.
Are there other alternatives to that sort of thing? So I wouldn't be surprised if some enterprise systems or enterprise organisations lock out that.
Yeah, absolutely. So we always try to be as specific as possible. So a CDC connector for a particular flavour of database. But then we go to sort of like, if that's not possible, we might drop down to JDBC or something like that. So we're actually querying the SQL interface. Now, that's not ideal because quite often the very reason you're integrating with Kafka is to remove load from the database. Yeah. But the net result of Kafka querying once and then serving all of the other queries often actually it improves the database performance.
And at least with the logs, you know what point it is, whereas JDBC, you basically...
Well, JDBC relies on an updated timestamp in the database.
Yeah.
So the query needs to support the idea of give me all the records from this timestamp. Yep. Yep. Yeah. Yep.
Business intelligence. Is there anything that we can use to actually visualize this data as in real time?
Yeah, like so. Actually, define more what you mean by kind of like to visualize or to kind of like.
Yeah. So just a question. So your topic.
Yep.
It's like a DB, right? It's like a database.
Oh no, we would refer to it as just basically a log of events. Yeah.
I know, but if we talk about say the global 360 topic, could the BI solution hook into it and look at it as if it was a data table? Therefore.
Yeah, absolutely. And so that would be actually, like, I mean, stream processing on stateful aggregation over the top. I think I've got to get out so somebody else can plug in. Yeah. But yeah, so that stateful aggregation can actually be used to drive sort of like, whatever system downstream you want. You might build some kind of React interface against it, or you might actually push it into another tool that visualizes that. But we can talk about that later if you want. Yeah. Cool. Thanks.